In this video, I am going to show you how to find deflection at a point of a cantilever beam using moment area method. And this is the example too. So this is the problem. It says determine the deflection at points B and C of the beam shown in the figure. Values for the moment of inertia of each segment are indicated in the figure. Value of E is given. So you can see beam here. This beam is fixed at A and all the lengths are given in here 4 meters and 3 meters. And at C there is a moment of 500 Newton meters and moment of inertia are given in this figure IAB and IBC. When we talking about moment area method, there are two theorems. So in example 1 we used theorem 1 for finding slopes. So in this example they are asking finding deflection, therefore we have to use theorem 2. So we'll see how we find deflections using theorem 2 of this moment area method. So this is the beam. First we have to find support reactions. So since this beam is fixed at A, we have to mark three components, which are two force components and one moment components. So I will mark it right here. So this capital M is the moment and X and Y are the support reactions. So first I will consider sum of all the horizontal forces. Since there are no other horizontal forces than this X, we can say X is equals to 0. And also if we consider vertical forces, there are no other vertical forces, therefore Y is also equals to 0. Next I am going to take moment about point A to the clockwise direction. If I take moments, I will have this capital M and this 500 Newton meters. So we can say M is equals 500 Newton meters. So this is the free body diagram. So next we have to draw bending moment diagram. So as you can see, there are two moment of inertias in this figure. But when we draw in bending moment diagram, we don't have to consider moment of inertia. So we just have to consider this overall beam as it's one beam. So you can see here I redraw it like this as a one beam. So you can see there are two moments at A 500 Newton meters and at C 500 Newton meters, and beam length is 7 meters. So it's simple beam. We can easily draw a bending moment diagram for this beam. For that I will cut this beam like this and mark this distance as X. So you can see that cut part. So at A there is a moment and distance to this point is X, and this is the shear force and this is the bending moment. Next I am going to find this moment capital M. So for that I am going to take moment about point A. If I take moments, I will have M equals 500 Newton meters. This is the bending moment diagram equation. So it's very simple. It's like Y equals C. So I will show you how we draw bending moment diagram for this simple equation. So this bending moment diagram will be like this. It's a horizontal straight line and this value will be 500 Newton meters. This is the bending moment diagram. Actually we have to find M over EI diagram. Here you can see IAB is equals 8 times 10 to the power 6 and IBC is equals 4 times 10 to the power 6. So IAB is equals 2 times IBC, right? So therefore I will write IBC is equals to capital I and then IAB is equals to 2I. So when IBC is equals to capital I, IAB is equals to 2I. When I draw M over EI diagram, it will be like this. So you can see this value is 500 Newton meters. When I divide it by 2 over EI, it comes 250 over EI. Because in this part, this AB part, IAB is equals to 2I as I showed you before, and BC part I is equals to capital I. Therefore we have to draw M over EI diagram like this. So this is the complete M over EI diagram. So you can see they are marked M over EI BC. They mark IBC instead of capital I. It doesn't matter. If you want, you can write M over EI. Okay, next we will see how we find deflections using moment area method theorem 2. For that we have to know deflected shape. So you can see this is a fixed beam. So there are no other point loads or forces on this beam. If we give a moment to point C to the counterclockwise direction, it will deflect like this, right? So this is the deflected shape. You can see it in this blue line. So you can see point A, B and C. Then I am going to mark tangent line of these points. So first I consider point A. So as you know, this point A is fixed, therefore no slopes or deflection at point A. If I draw a tangent line, it will be a straight horizontal line. So I will mark it as tan A. Then if I draw tangent line at B, it will go like this. So I will mark it as tan B. Also point C, if I draw a tangent line at C, it will go like this. I will mark it as tan C. Next I am going to mark deflections. So at A there are no deflections. At B there is a small deflection. I will mark it respect to this tan A. So I can label it as delta B, which is deflection of point B, is equals to TB respect to A, because tan A is the initial state of this beam before deflected. So therefore I can write delta B is equals to TB respect to A. Also point C, I can write deflection of point C as delta C equals TC respect to A. So like this. So that's how we mark deflections of points respect to tan A. Next we will see how we find these deflections. So this is the theorem 2. I am not going to read this whole paragraph. You can read it. I will show you what is the idea of this theorem 2. First I am going to find delta B. So you can see here delta B is equals to TB respect to A. So there are two letters B and A. So that means we have to consider area between A and B. So this is our MOVA diagram. Area between A and B is this area. So in order to find the deflection of point B or delta B, we have to consider this area. This area means area between B and A. So I will find the area here. So delta B is equals to, this is a rectangle, so this length is 4 meters times this height is 250 over EI BC. So this is the area. Next I have to take moment about one point. So you can see there are two letters now, B and A. B is left side letter, A is the right side letter. We have to take moment about this left side letter, which is B. That means I have to take moment about this point B to this area, right? So next I am going to take moments. I am going to take moment about this point B, and this is a rectangle, and centroid of this rectangle is lay on middle of this rectangle. So this AB length is 4 meters. Half of the 4 meters is 2 meters. Therefore I have to multiply this by 2 meters. So this is the deflection of point B. So you can see delta B is equals to TB respect to A equals 250 over EI BC times 4 times 2. So this is the deflection of point B. You can substitute E value and IBC value, and you can simplify it and get an answer for delta B equals 2.5 millimeters. Next I am going to find delta C. So delta C is equals to TC respect to A. So there are two letters C and A. Therefore we have to consider area between C and A. Area between C and A is, this is A, this is C, this is whole diagram. So therefore we have to consider this area as well as this area, and also we have to take moments now. For that we have to take moment about this point C, which is left hand side later. So I have to take moment about this point C. So this is a rectangle I told you before now. So this is also a rectangle and a symmetric one. This rectangle also symmetric, and here also centroid of this rectangle is lay on middle of the rectangle. So BC length is 3 meters, half of 3 is 1.5 meters. So this length is 1.5 meters. So next I am going to write the equation delta C is equals to, here I have to consider these two parts separately. First I consider this part. So area of this small rectangle is 4 times 250 over EIBC, and distance to centroid is, this is the centroid, this length is 2 meters, this length is 3 meters, 2 plus 3 equals 5. Then I will consider this rectangle. So here area is, BC length is 3 meters and this rectangle height is 500 over EIBC. And distance to centroid is 1.5 meters. So this is the deflection of point C. You can see clearly wrote equation delta C is equals to TC respect to A equals and 250 over EIBC times 4 times 5 plus 500 over EIBC times 3 times 1.5 meters. So if you simplify this, you can have 7250 over EIBC. So you can easily substitute values for E and IBC. Then you will have delta C is equals to 9.06 millimeters. Since both answers are positive, they indicate that point B and C lie above the tangent at A. So that's how we find deflections using moment area method theorem 2. Please like, comment and share this video. To watch future educational videos, please subscribe Educate Today YouTube channel. Thank you.